Okay, so moving on to section 1.8. This section talks about the subsets of real numbers. This is something that you probably haven't seen a whole lot of before, and something that you might not necessarily see a whole lot of again, but excuse me, I think it's important just to at least look at it, and have an idea of what's being talked about, because it could show up anywhere, and it will absolutely show up in college if you pursue any type of math in college. So uh, the subsets, basically, the definitions that they explain in here are going to pretty much say it all. But a set is a collection of objects or things, and the objects in the set are called elements. And I'll always say elements, and you'll see why in a second. But uh, at the very beginning there of that definition, they show you. Get this. They show you some notation. Okay, and it looks like this. It looks like a kind of a weird E. Okay, so this would be read that X is an element of A. So A is going to be our set, and X is going to be an element of that set. So, you can define sets to be anything, and it could be, a set of all real numbers. It could be a set of integers. It could be, anything. It could be just a set of, let's say, it could be anything. I mean, it could be, smiley face, whatever you want it to be. So in the set A, we have x, 1, 2, 5, smiley face. So the elements of A are those objects. And then we see that x is obviously an element of A because x is in A. All right. So now let's say that B is x, 2, 8, frown face. All right. The two things that they really stress in this book, and the two things that are probably most important when you're talking about sets, are going to be intersection and union. All right. So we know what the elements of each set are. It's just the objects within the set. So set A, the elements are right here. Set B, the elements are right here. Now we have union and intersection. And they show you this as a Venn diagram. They show it to you a couple different ways. Basically, what you need to remember is that the union symbol is this. Okay, so basically it looks like a U. The intersection is just that flipped upside down. So I think of it as U for union, in for intersection. However you want to remember it is up to you. It doesn't matter to me. And then the important word to associate with each of those things is, for the union, you're going to remember the word or. For the intersection, you're going to remember the word and. Okay, so anytime we see union, we're immediately thinking or. Anytime we see intersection, we're immediately thinking and. So if I said, what is the union of A and B? So sets A and B, I want to know any element that is in A or is in B. So that means if the element is in A, you're going to write it down. If the element is in B, you're going to write it down. But we don't have to repeat elements. So since both of them contain X, I just write X one time. So I would say that A union B is X. A contains 1. They both contain 2. A contains 5, smiley face. B contains 8, frowny face. I keep doing parentheses, there should be brackets. Okay, so that's the intersection because it's everything that is in A or B. All right? If I want that was the union, everything that's in A or B. If I want the intersection, so A intersect B, I want to know everything that's in A and in B. Okay, so for the intersection, it's the things that are contained only in both of them. So if I want A intersect B, I want the things that only show up in both. So x shows up in both, so that's going to be in the intersection. 1 does not show up in both. 2 shows up in both. 5 doesn't show up in both. 8 doesn't show up in both. Smiley face, frown face. Okay, so for the intersection, it would just be x and 2. All right, so if you're looking at that as a Venn diagram, for the intersection, let's do, so we have intersection, we have union. This would be everything, right? So this is set A, this is set B. Anything that's in A or B. This one, this is A, this is B. The intersection would be anything that's in both of them. So it's just this right here. I hope that makes sense. Let's look at some more examples of this. Okay, so if we look, let's look back at the problems in the back of this. So the very first set of problems, they say the following problems: A is this set, B is this set, C is this set, and then they start asking, okay, what's the union of A and B? So you list everything that's in A, everything that's in B. What's the intersection of A and B? You list only the things that show up in both A and B. 2 shows up in both A and B. 4 shows up in A and B. And that's it. Okay? Moving on. So from there, they move into prime numbers and factoring. And actually, before we get into that, the last kind of thing that I want to talk about is the null set or the empty set. So let's say that A is 1, 2, 3. B is 4, 5, 6. Okay, the union of these two obviously would be 1, 2, 3, 4, 5, 6. The intersection, there's nothing that is in both A and B. So the intersection of A and B would be what we call the empty set, or the null set. Okay, that means that there's no elements in that set. So since there's nothing that's in both A and B, then there's nothing in this set. Okay. All right, so moving on. Next we talk about prime numbers and factoring. And basically this is just to get a quick intro into what a prime number is and what prime factorization is. And this is like factor tree stuff, right? So this is old school, probably middle school stuff if I had to guess. But a prime number by definition is any positive integer larger than 1 whose only positive factors are itself and 1. So with any number, so let's say 12, if I can break that down into factors, okay, if I can take two whole numbers, multiply them together to get 12, that's what I'm trying to do. So when I do my prime factorization, I just pick any two factors of 12. You could do 3 and 4, you could do 6 and 2. You could do 1 and 12, but that'd be pointless because you could just keep going forever. So if we do 3 and 4, the question is, can I break 3 down to anything other than 3 and 1? And since the answer is no, we know that that is a prime number. So I circle it. With 4, can I break 4 down to anything other than 4 and 1? The answer is yes. I can break it down to 2 times 2. Can I go any further with these? No. Okay, because I can't multiply anything together to get 2 other than 2 and 1. So my prime factorization for 12 would be 2 times 2 times 3, which we can write as 2 squared times 3. Okay? If you started with a prime number, if you started with, say, 7, obviously there are no factors of 7 other than 1 and 7, so I'm finished. Okay, I can't go any further, so 7 is a prime number. And that's all that they're explaining on pages 62 and 63. It's stuff that I'm sure you have seen before. So for your prime factorization, start with the number, do the factor tree. When you get to all prime numbers, okay, when there's only prime numbers left, you can't go any further, circle them, and then we write them out as a multiplication problem. Now to get to this, all I did was, since I had 2 times 2, it's the same as 2 squared. It's just an easier, simpler way to write it. For this one, it wouldn't really matter that much, but if you had 2 to the 5th times 3, it looks a lot cleaner to write that than 2 times 2 times 2 times 2 times 2 times 3. Okay? And I think that will get us through 1.8.